And okay, so I'd like to introduce Bhargav Bhatt again from the Institute for Advanced Study and Princeton University, who will give his third lecture in his series on p-adic Hodge theory and algebraic geometry. So yeah, please go ahead.
Great. Yeah, thank you very much. Thanks again for the invitation, and to those of you that stuck around till the end of the 3-week event, thank you. So I wanted to correct one misconception or one incorrect thing I said yesterday, which was I mentioned this theorem of Petrov about when the Hodge state stack is split after Frobenius pullback, and then deducing these consequences about F splitting. I said there was no stacky proof of it, and that was incorrect. So I looked back at my email, and then actually in the email that Sasha told me about this, he also explained non-stacky proof using the algebra of differential operators. And maybe this is also due to Vologodsky. So I wanted to correct that. Okay, and then so on to business for today. I want to talk about the Simpson correspondence in the p-adic setting. So with the complex numbers, the Simpson correspondence, or maybe Simpson is kind of the final word on the subject, but there's a long history of names associated to this. I won't name all of them here. You can find more about it in the first week in Davish Maulik's talk, but the statement that's relevant for us is the statement of equivalence of categories proven by Simpson. And he proves that for a for a smooth projective variety over the complex numbers, the category of complex local systems on it is identified with the category of semi-stable Higgs bundles with vanishing Chern classes. And so this gives two very different perspectives on the same object. One is very topological, and one is very algebro-geometric. And what I want to talk about today is what the p-adic analog of this theorem looks like. This is an area that was initiated by Faltings about 20 years ago, and it's seen a fair amount of progress in the last few years. Okay, so that's what we're doing. And then in the last 10 minutes of the talk, I'll try to explain some more recent mathematics that has come out of it. Let's get into it. So what's the setup? My setup is going to be that C over QP is a perfectoid field. And feel free to assume it's just an algebraically closed p-adic field, like CP. And X over C is going to be a smooth rigid analytic variety, or a smooth rigid space. Feel free to assume X is an algebraic variety, although it's going to be important for the theorem to treat it as a rigid analytic space, because one of the sides is going to be an analytic category. And I'll elaborate more on that as I go along. And so the starting point of this investigation is construction that goes back to Faltings and was really clarified by Scholze, that explains that there's an extremely natural way to take topological data like a local system on X and attach to it some more coherent data. And so this goes through the pro-étal site. And so let me recall what the picture over here is. So X has a pro-étal site, which you can think of roughly as the site whose objects are given by projective systems of étal maps over X, rather than just a single étal map over X. A typical example would be you have something étal over X, and then a whole tower of finite étal covers over it. And what this tower lets you do is it lets you trivialize infinite local systems, ZP local systems, rather than just local systems with finite coefficients. And so the practical consequence is that it allows you to write down the following functor. So there exists, it turns out to be a faithful tensor functor, which goes from the category of ZP local systems on X in the étal topology. So compatible systems with Z mod P to the N local systems, if you like, to vector bundles on X pro étal. And when for experts, when I talk about vector bundles on X pro étal, I always mean with respect to the completed structure sheaf. And the functor is actually very simple. It's just, sorry, let me make this arrow a little longer. L goes to L tensored over ZP with OX plus hat. Or just OX hat, sorry, no plus. Okay, so It's like what happens over the complex numbers when you take a local system and produce a flat connection out of it. The important point is that this sheaf over here trivializes a local system, so it makes sense to write this down. And just by virtue of how it's defined, the right-hand side is linear over the ground field, C. And so you can just formally extend scalars to C, and you get a functor like this. And this functor has some really nice properties. So I already said it was a faithful tensor functor, and it's even fully faithful in some nice situations. So, which is fully faithful, even at the derived level. So even at the level of cohomology, if X is proper and C is algebraically closed. Okay, so if you're thinking about smooth projective varieties over an algebraically closed field, then we already have a very good mechanism for turning a local system into something coherent looking. And so if you want a Simpson correspondence, it would be reasonable to try to just understand this category in terms of Higgs bundles, because you already have a mechanism for moving the topology into something more algebra looking. And that's what we're going to do. And so let me tell you the theorem that we proved about this, and then I'll elaborate more on its history. So theorem. So this is a joint work with Mingjia Zheng. And what we prove is that the picture is almost as good as that over the complex numbers, except there's a twist. So there exists a natural GM gerb. So there's a Brouwer class, if you like, over the cotangent bundle of X. And secretly, there should be a Tate twist on the cotangent bundle, but let me suppress it in the talk. So there's a natural GM gerb P to T star X, plus an equivalence of categories between perfect complexes on the pro-Étale side. So I'm already formulating statements at the derived level with Higgs bundles, which are twisted by P. So let me just make the notation and then say what it is. So this is Higgs X comma P. And so what does this actually mean? The right-hand side is going to be those complexes that are coherent complexes on the cotangent bundle, which have finite support over X. And they're twisted by the gerb P, sorry. So, well, okay, let me just actually say it more, write it down instead of just using symbols. So these are objects on T star X that are twisted by the gerb. And the property they have is that the support of K of this complex is finite over X. Okay, so here's a picture for what's going on. So if I give you such a K, what does its support look like? You're supposed to think about subsets of T star X. So here's T star X. It has a projection map to X. And the support looks like something like this, Z. And so these supports that show up this way are often called spectral varieties, because in the case of curves, they were spectral curves that were studied by Hitchin when you're studying the Hitchin fibration. And the statement is that if I give you any sheaf on the cotangent bundle whose support looks like this, it corresponds to a perfect complex on the pro-Étale side, with the one twist that you don't actually work with sheaves on the cotangent bundle, rather you work with twisted sheaves, where the twist comes from this gerb. Okay, so this is the statement. I want to spend some time extracting more honest consequences out of the statement. And so the first thing to note is that because of the twist, if you want to get honest consequences involving Higgs bundles, you basically need to figure out how to make the twist go away. And so the game then becomes to understand the loci on the cotangent bundle where the gerb is actually split. What can you say about splitting P? And so let me make some comments on this. Remarks. These are mostly just remarks about the gerb P. So the first remark is that this gerb P is actually multiplicative on the fibers. So if I fix a point downstairs, the fiber is a vector space, and I have a family of GM gerbs on this vector space. And the statement that it's multiplicative means that it's compatible with addition. So if I give you a GM gerb at point A and a GM gerb at a point B, then the gerb I have at point A plus B is the sum of those two gerbs. And so a formal way to write this is that if you think about the classifying map of the gerb, it's something that goes to B squared GM. This is just a tautology. For B squared GM is the object that classifying GM gerbs. And the statement is that this is additive. And so in particular, what this implies is that P is canonically trivial on the zero section. Because it's a group homomorphism, so on zero, it's canonically zero. And so going back to this equivalence, if you restrict to those twisted Higgs bundles that are genuinely supported on the zero section, those are just untwisted Higgs bundles. But also the Higgs field is zero because they're supported on the zero section. So those are just perfect complexes on X. And similarly, since the pro-étal side maps down to X, a perfect complex on X gives you something on the pro-étal side. And those two constructions match up under this equivalence. So that's kind of the most trivial example of what this equivalence is doing. Oh yeah, sorry, let me give this equivalence a name. I'll call this S, S for Simpson. And we call this the Simpson gerb. Oops. Okay, so that was kind of a simple thing to say about the gerb. You might wonder if the gerb is necessary at all. Like maybe we're just, being stupid and the gerb is actually always trivial. And that's actually not true. So P is in fact always non-trivial. P is non-trivial and in fact always has infinite order. Well, okay, as long as X is non-trivial. So if the dimension of X is positive. And so because it has infinite order, this means it cannot be algebraic. And so P is genuinely analytic. Because if you had a GM gerb on a smooth variety, in the algebraic sense, it would always be torsion. But this one has infinite order. So this is some analytic object. And this is why I said it was important to treat X as an analytic variety from the start. Okay, so what can you actually say about trivializing P then? It's not trivial on the entire cotangent bundle. It is trivial in the zero section. Are there other loci where it's trivial? And this was actually the starting point of our work. So there's a remarkable theorem of Ben Hoyer from a few years ago that generalizes work of Faltings from 2005, which was not formulated in these terms. But once you know about the gerb, it can be formulated as follows. So let me explain what they do. So this is Faltings for curves, and then Hoyer in any dimension. So let us make some nice assumptions. So assume X over C is proper, and C is algebraically closed. They're going to trivialize the gerb on many subsets of T star X. And in order to do that, you need two choices. So I'm going to fix two pieces of data. One is a B2 lift of X. I don't want to spend too much time on this. If you're familiar with characteristic P geometry, a natural structure to ask on a characteristic P variety is a lift of it to Z mod P squared. This is the analogous structure in an equal characteristic zero field. So B2 is some canonical square zero thickening of C, and you're asking for a lift there. Now, since you're in characteristic zero, such thickenings are always split, so there's always some lift, but you have to fix the lift, and the construction I'm about to do is going to depend on the lift. And the second piece of data, which is maybe slightly less nice, is an exponential for the field C. So this is a splitting of the logarithm map. So if you're in the p-adic setting, there's a logarithm map which goes from 1 plus the maximal ideal of C down to C, and you demand a splitting of this that you call the exponential. The p-adic exponential converges on some small ball. And so inside a small ball over here, there already is a nice section, and you're choosing some extension of it to the entirety of C. Such a choice cannot be made Galois equivalently if there was a Galois group around, but c'est la vie. And then the conclusion is P can be trivialized on all spectral varieties at once. And so one way to write this is that you look at the union over all Z, where Z is a subset of C star X finite over X. So any Higgs bundle, any twisted Higgs bundle that shows up is going to be supported on one of these Z's by definition of what a twisted Higgs bundle was. And so since P can be trivialized on this, once you choose such a trivialization, what it means is that you can ignore the twist. In the theorem. And so you get a genuine equivalence between local systems in the Étale topology and Higgs bundles, which is pro-Étale local systems and Higgs bundles. So this is extremely analogous to what happens over the complex numbers. Let me continue making some remarks about this. So this was, actually the genesis of this work is that we had a seminar on Ben Hoyer's work. And it was through the seminar that at least I learned that in order to understand the p-adic Simpson correspondence, it was very fruitful to work locally on T star X rather than on X. And then we were trying to understand what are the choices that go into it, or what's a good way to sort of repackage this information. And we ended up with this statement, which I like because it doesn't assume X is proper and it doesn't need algebraic closedness or any additional choices. Okay. Right. So another thing to say in a related vein is that there is a lot of work in this area, and I'm not summarizing it here. So Falding's paper appeared in 2005, and there were a whole series of papers that followed it by various authors that sort of probed more and more of the structure of the Simpson correspondence until Hoyer proved this theorem. And related to what I'm about to say is there's also ongoing work of Anschutz, Lebras, Juan Esteban Rodriguez Camargo, and Peter Scholze, which gives what seems to be a Cartier dual description of this equivalence. And so instead of this GM gerb, they're able to write down what its Cartier dual should be, which is the analytic Hodge state stack. And then the theorem is some very simple sounding statement that perfect complexes on X pro Étale and the analytic Hodge state stack are the same. But that's my guess as to what is being proven. And then finally, the biggest open question in the subject is what happens to the genuine representations? So let me go back up here. I said earlier that we have this functor from local systems to vector bundles. And then from that point on, I basically forgot about this side and just worked on this side and even at the derived level. But you might wonder that what happens to the actual local systems under this equivalence? Like on the left-hand side, I have the stuff coming from genuine local systems. What does that correspond to on the right-hand side? And we don't know. So the essential image is still mysterious. There are some partial results on what it could be or what it could not be. Optimistic conjecture is that when C is CP, the essential image might be exactly the same as what happens over the complex numbers. So semi-stable Higgs bundles with vanishing Chern classes. But I don't think there's a definitive result along those lines yet. Okay, so these are some remarks I wanted to make about the gerb. What I want to do next is I want to tell you an epsilon about how the theorem is proven. And this is mostly to explain how it's like very closely related to what I told you about in the first two talks, even though the setup is slightly different. But maybe before I do that, are there any questions I could answer? This might be a good point.
We don't see any questions, so go ahead.
All right, thank you. Okay, so I want to explain how you might go about relating objects on the pro-Étale site to Higgs bundles. Like, where does the cotangent bundle come in? And so what I want to try to explain to you is how to define a functor in this direction. So how to define S inverse. So I'm gonna I'm gonna assume that X has a nice model, and then there's a sheafification argument to say that you don't actually need to assume this. And so here's how I want to do this. So suffices to show the following. So say X math frac X over OC is some smooth or log smooth formal scheme. And X, the variety in question, is the generic fiber of this. What we want is to construct a functor S inverse, which goes from these twisted Higgs bundles, so coherent sheaves with finite support on the cotangent bundle twisted by the gerb P, into perfect complexes on the pro-étale side of X. And I want to explain how both sides have interpretation in terms of this model that is in terms of objects we've already encountered previously. And so maybe the first remark I want to make is we can actually simplify our task slightly, which is instead of defining the functor like this, which is from Higgs bundles supported on the entire cotangent bundle of X into the pro-étale side, I can restrict myself to a locus. So let me put less than 1 over here. And so what do I mean by less than 1? So this is the locus of the cotangent bundle consisting of those cotangent vectors which are distance less than 1 from the origin. To have a notion of distance on a rigid variety, you need an integral model of that variety, and I've already fixed such an integral model. And so this notion of less than or equal to 1 is with respect to this integral model. And so what this lets me do is the, oh yeah, I'm sorry, I have to explain why it's enough to define a functor out of this category. So I was trying to define a functor from all twisted Higgs bundles, which could be supported anywhere in the cotangent bundle, really far away from the 0 section. And I'm saying it suffices to do it just for the ones which are sufficiently close to the 0 section. And the reason for this is an observation essentially due to Faltings, that if you're trying to do something étale local in the rigid topology, then you can make things as small as possible. There are étale covers of rigid varieties, which at the level of integral models are extremely ramified at the integral level. And being extremely ramified at the integral level means that the tangent vectors on the source and the tangent vectors on the target have very incompatible notion of distances. And so any cotangent vector on any rigid variety becomes very small after you pull it back along a sufficiently big étale cover. And since the target you're trying to map into is something which has nice étale descent properties, it's enough to define the functor out of these objects. And so now let's actually do it. So so the left-hand side is roughly, and I'll comment on what I mean by roughly what, is just the generic fiber of the corresponding integral version. So if you remember the talk yesterday, I mentioned to you that whenever I give you a smooth formal scheme over a perfectoid ring, there is this canonical GM gerb on its completed cotangent bundle that I also called P yesterday. And the compatibility I'm using here is that this object is compatible with this object when you invert P. And so the left-hand side has a nice integral model, which is just coherent sheaves on the twisted cotangent integral bundle. And from last time, so from yesterday's talk, this was the same as perfect complexes on the Hodge state stack X, also with P inverted. On the other hand, the right-hand side is the same as perfect complexes on the stack I introduced in the first lecture. So I had this perfectoidization, and if you work with the almost version of it, and you consider perfect complexes there, one can show that these are the same as perfect complexes on the pro-étale side. And so, in fact, this is some of the work you have to do in order to construct this Riemann Hilbert functor I was talking about in the first talk. And so the upshot of all of this at the level of symbols is we were trying to define a map from the left-hand side to the right-hand side. I have now explained to you that the left-hand side is perfect complexes on the Hodge state stack. And sorry, this should have been math frac X. And the right-hand side is perfect complexes on the perfectoidization. And then the functor is just pullback. So now you just use pullback. And so that's how you get the functor, and a more careful analysis of what's going on at each step of this construction you can actually use to prove the entire theorem. Again, the details are not so necessary. What I'm trying to say is that yesterday's theorem about smooth formal schemes over a perfectoid ring had an equivalence which looked very similar to what we were trying to prove. It involved a GM germ on a cotangent bundle, and it involves perfect complexes on the Hodge state stack. And essentially, if you turn on the étale topology on the generic fiber and sheafify that equivalence, you get the Simpson equivalence I was talking about at the start of today. So that's the story with the Simpson correspondence. That's how the functor is defined, and I told you a little bit about the germ along the way. And so what I want to spend the rest of the talk doing, and today I'll try to be on time. So I want to forget about the proof. I just want to try to understand how this germ specializes when you specialize X to characteristic P. And so here's the question I want to address for the rest of the talk. And so no more rigid geometry in the talk. Sorry, is there a question? This will also be a good time to ask questions.
No, I think it's just a little bit of background on
The music. Okay. All right, so let's put the Simpson correspondence aside for the moment. Let me explain first. Recall a very beautiful story from characteristic P geometry. So I want to convince you that what I've written down is actually something completely natural from the point of view of things already known in characteristic P. So let's say K is a perfect field of characteristic P. X over K is a smooth variety. And I'm going to talk about D modules in characteristic P. So D X over K is going to be the sheaf of crystalline differential operators on X. And crystalline over here just means you should not be worried about it. These are not funny differential operators. These are just the obvious ones you would want to write down. So for affine n space, I'm just talking about the Weil algebra and n variables. You have the n polynomial variables, and then you have d by dxi for each variable, and then the obvious commutation relation. Nothing funny about divided powers. So this is the sheaf of differential operators I want to talk about. The starting point of trying to understand the analog of the Simpson correspondence in characteristic P is this theorem of Bezrukovnikov, Merkovich, and Ruminin. Bezrukovnikov, Merkovich, Ruminin. And what they proved is that unlike what happens in characteristic 0, this sheaf is extremely close to a commutative ring. This ring is extremely close to being commutative. More precisely, it's Azumaya over a commutative ring. So first, they identify what the center is. And the center of the ring of differential operators is functions in the cotangent bundle of X with the Frobenius twist. And the way you take a tangent field and produce an element of the center is via the p curvature. So this is via the p curvature map. The right-hand side, I remind you, is the algebra of functions in the cotangent bundle. And then moreover, the second part of the theorem is that D is Azumaya over the center. And so an upshot of this in terms of symbols is that if you're interested in the category of D modules on X over K, it's just quasi-coherent sheaves on the cotangent bundle twisted by a gerb. And this gerb is the gerb corresponding to D. Okay, so this is should maybe look similar to what I was trying to prove in characteristic 0, One side is just quasi-coherent sheaves on the cotangent bundle with a GM gerb twist. And the other side was some category that was more topological in nature. It's D modules in this case. In the Kersig 0 case, it was perfect complexes on the Pro-Étale side. Okay, so this is their theorem. And then moreover, there's another companion observation that goes along with it, which is extremely useful, which is that this gerb is never trivial. So P is always non-trivial. And this is quite simple in this case. Well, okay, if the dimension is again positive, in case Gabor watches this talk and complains. So the reason for this is extremely simple. The sheaf of crystalline differential operators can be thought of as a non-commutative version of a polynomial ring. More precisely, it has a filtration, and the associated graded is a polynomial ring. Now, a polynomial ring has no zero divisors. And so you can use that to prove that the sheaf of differential operators also has no zero divisors. And therefore, it cannot be a matrix algebra. That's the idea of the proof. It's simple algebraic observation. But it's useful because it's telling you that this thing is never trivial. And so if eventually I want to use this to conclude that the Simpson gerb in Kersig 0 was also non-trivial. Oh, sorry, I got ahead of myself, right. If you want to use this equivalence over here to extract some more tangible consequences, you again need to figure out how to trivialize P. Once you get rid of P, you'll get an equivalence between some honest class of D modules and some honest class of Higgs bundles. And so this was the fact that you could do this and that you could do it in interesting cases was due to August Vologodsky. And so they proved many theorems, but I'll just say one of them over here in their work on non-abelian Hodge theory and Kersig P. One thing they proved is the following. So if X lifts, to W2 of K, so to Z mod P squared, essentially, then it's not the case that P is trivial, but it is trivial on a small neighborhood of the zero section. P trivialize this. So not just is trivial, but can be trivialized using such a choice on the pth neighborhood of the zero section, pth infinitesimal neighborhood of the zero section. Inside P star X. And so what it means is that if you're interested in these twisted Higgs bundles that are supported in this infinitesimal neighborhood of the zero section, you can ignore the twist. And so they use that to conclude that one gets an equivalence of categories like this. If you look at Higgs bundles, where the Higgs field has order of nilpotence less than or equal to P minus 1, then those are the same as modules with integrable connection, whose P curvature is nilpotent of order less than or equal to P minus 1. And maybe there should be a twist somewhere. And so now it looks a lot like a Simpson correspondence, something having to do with D modules. MIC is the standard notation in the subject for modules with integrable connection. So modules with integrable connection with some nilpotence condition correspond to Higgs bundles with a very similar nilpotence condition. And in some sense, this is kind of an analog of what I was trying to say in Kersig 0, where once you know you can trivialize the gerb, you can extract consequences. Okay, so this is the story in Kersig P. As I said, it looks quite parallel to what happens in Kersig 0, with the following key difference, which is both on the generic fiber, I said there was a gerb on the full cotangent bundle. Similarly, on the special fiber, so in Kersig P, there's a gerb on the full cotangent bundle. But at the integral level, I have only told you that the gerb exists on the completed cotangent bundle. And so there's the following question that comes up if you want to relate both the Kersig 0 and P stories. So question. If you go back to our setup now of mixed characteristic, so if I give you a formal scheme over OC, let's say it's smooth, and fibers are, I'm going to write as X, Roman X is going to be the generic fiber, and X naught is the special fiber. So the question is there a GM gerb on T star X of the formal scheme that restricts to the two gerbs I know on the fibers. So the Simpson gerb on the generic fiber. Well, on the generic fiber of the cotangent bundle, the formal scheme, which means T star X less than or equal to 1. And the August-Wologotsky gerb that I just talked about on the special fiber. The theory of the Hodge stack that I discussed yesterday essentially says the answer to this question is yes, if you allow me to put a hat over here. So if I work on the completed cotangent bundle, there is a gerb, but now for the completed cotangent bundle, the locus you would get on the generic fiber would have a strict inequality over here, rather than a non-strict inequality. And it's really this question about this extension. Can you extend to the boundary of the unit disk that I'm asking over here? And it feels technical, but it's extremely, it's a rather non-trivial jump. So for example, if I tell you that this X has, let's say it's affine, then you can prove that the gerb you get on the completed cotangent bundle is actually always trivial. Not canonically, but it is trivial. On the other hand, I told you that the August-Wologotsky gerb was never trivial. And so in order to do something like this, you're going to have to construct this gerb that lives on the non-completed cotangent bundle, and it will not be trivial, even in the affine case. And so this was the question that at least motivated me to describe, to pursue the direction that I'm about to go into. And the answer essentially is yes. We figured this out in the last year. And I'm not going to be able to tell you everything about it, but I just want to give you a very rough flavor of what happens, because I think maybe the answer turns out to be more interesting than the question here. And so the answer is yes. And more precisely, it leads to the following following story. So I'm going to call this sheared prismatization. And so first, let me tell you the theorem, and then what it's a part of. And so this is ongoing work with Kanaev, Matthew, Wologotsky, and Mingjia. And the version I need to answer the question above is just is the following statement. So let's say if R is any perfectoid ring, in applications it's going to be something like OC. X over OC is a smooth scheme, smooth formal scheme. So then the statement is there exists a diagram like so. So here's X. Here's this Hodge stack I told you about yesterday. This Hodge stack was a torsor for the classifying stack of the tangent bundle sharp. Whoops, didn't mean to erase that. And the claim is that this torsor has a reductional structure group to something smaller. So that we call X Hodge state hat. And this reduction is a torsor over the completed version of TX sharp. And the Cartier dual to this state, so this is what we call the sheared Hodge state stack. And the Cartier dual to the statement from yesterday's talk is, sorry, the analog for the sheared Hodge state stack of the Cartier duality statement I mentioned yesterday is that the category of sheaves on the sheared Hodge state stack, quasi-coherent sheaves on the sheared Hodge state stack, is identified with the category of quasi-coherent sheaves on the cotangent bundle of X with respect to a gerb, some natural GM gerb. Note that there's no hat now on the cotangent bundle. And so this gerb over here is providing an answer to this question that I raised on the previous page. And so if you like, it's just a non-trivial statement about the Hodge state stack. It's saying that you had some torsor for some group, and here's a smaller group that maps to that group, and we're constructing a reductional structure group for the torsor. And in fact, what really happens is that there is a sheared version of the full prismatic formalism, not just the sheared Hodge state stack. And so more generally, we have a sheared prismatization construction. So everything that we've done so far with prismatic blank now has a sheared analog. And so I'm not going to tell you how this works in any great amount of detail, but I will tell you the key definition you need in order to do this yourself. So here's a definition. So first, let me recall. So okay, maybe let me tell you what the format of the construction is before I get into it. So yesterday I gave this definition of the prismatization, which was some construction involving the bit vectors, and then there was a whole series of things you could do with it. And so to do the sheared version of the construction, it turns out that the best way to do it is to modify the bit vectors to something slightly different that maps to the bit vectors. And so I'm going to tell you what this modification is. So recall, first of all, that there is a natural ideal in the bit vectors, which is called W hat. So W hat of a ring R is those bit vectors A0, A1, dot, 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 in W of R, where each AI is nilpotent. And it's 0 if I is sufficiently large. So only finitely many components of the bit vector are non-zero, and each of those non-zero components has to be nilpotent. And so this inside W of R is an ideal, it turns out. And so using this this ideal, one can define the following variant of the bit vectors, which we call the sheared bit vectors. So the sheared bit vectors of R, it's a ring. It's going to map to the bit vectors of R, and it's going to be defined by a fiber product. So W of R maps to W of R mod W hat of R, because I can mod out by ideals. Now this ideal that I mentioned, W hat of R, is actually stable under Frobenius. And so what you can do is you can contemplate its inverse limit perfection under the Frobenius. And then look at this fiber product. So this is the key definition. These are the sheared bit vectors. And now the exercise one has to do, which is rather long, and we're in the process of carrying out, is you replace W with sheared W in all papers on prismatic cohomology. And it turns out in most cases it works. And actually, in most cases, you get a slightly better statement than you did for the non-shear story. The case in point being the one I just explained, where the sheared Hodge stack is nicer in the sense that it sees more sheaves than the usual Hodge stack sees. The usual Hodge stack was only seeing those sheaves that were supported set theoretically close to the 0 section. But the sheared one sees sheaves on the entire cotangent bundle. And there are other statements like this that I could mention. But I actually didn't want to say too much more about this today, except maybe I should just make one comment about this, is that this perspective that I just presented was suggested by Drinfeld. So in our original approach to sheared prismatization, we were just working with the prismatic theories for W bar. Like essentially, this is a fiber product diagram, and we were working with the other 3 terms of the fiber product, but we sort of missed that you could form the fiber product and work there. And then Drinfeld suggested doing that. And then if you do that, sort of just psychologically feels a lot nicer. Okay, so I think I actually didn't want to say much more. And since it's the last talk, I figured no one will complain if I end early. So I will stop here. Thanks again for listening to me.
So thank you very much, Bhargav, for the really great lecture series. Let's see if there are questions here. Yeah.
So thanks for the great talk, and for this series. So because there's the sheared prismatization, is there a sheared perfectization, and is there a notion of sheared perfective ring? And if so, it's interesting.
Okay, thank you. Thanks for the question. There is a sheared prismatization, but it turns out that the sheared perfectoidization that you would write down agrees with the usual perfectoidization. So the sheared story and the non-sheared story are somehow they map to each other via Frobenius. And so if you're working in some regime where Frobenius has been inverted, you do not see the difference between them. So yeah, there's no, you don't see a new notion of a shared perfectoid ring.
Hi, Bob. So is there a compatibility between the function control media to the p-adic remainder function from the Rham local system to the module?
So, sorry, could you just say the question more slowly?
Compatibility between the p-adic remainder function to the Simpson function, the Simpson correspondence you constructed. Like the one I had in mind is go from the Rham local system to filter D modules over X. Over complex centers, in almost half Hodge case, you can go from filter D modules to big complex. One is a mixed characteristic animal list.
Okay, so sorry, the audio wasn't that great. If I understood the question, it was about how to relate what I've talked about today, say, to the fact that if I give you a de Rham local system, you can also extract a filtered D module out of it.
Yeah.
Yeah, so the two are related in the natural way. So if I give you a filtered D module, you can look at its associated graded. The associated graded is then a graded Higgs bundle. And if you apply the Simpson correspondence to the corresponding local system, you would get the same Higgs bundle, but without the grading now.
Yes.
Mm-hmm.
Sorry, maybe this is a follow-up to the question that was just up, but the Boreal bundles, they have a natural deformation, either across local systems or for the Boreal site. Do you have a description of it and show us some twisting if it could happen?
Again, sorry, I'm not fully hearing the questions, but if I understood correctly, it was about trying to deform this equivalence in the beta Rham plus direction.
That's right, exactly.
Yeah, good question. I am thinking about it, but I don't have a clean statement to make right now. I mean, sorry, there are statements you could make if you restrict attention to the kind of local systems you work with. Like essentially, if you work in, for example, if you work with the nilpotent guys, then you can ignore the twist. And then there are statements you can make involving T connections, which I think you probably know if I guessed the voice correctly. But I don't know how to sort of deform the full gerb in the beta Rham plus direction. On the other hand, I'm optimistic that this p-adic Simpson story that that's on the screen right now, it actually works not just for perfect complexes, but all quasi-coherent sheaves on the perfectoidization. So I believe I know how to write down sheaves on objects here attached to constructible sheaves, not just local systems. And I'm interested in understanding how this deforms in the beta Rham plus direction, but I don't have a clean story to say yet.
Thank you very much.
So this is a follow-up to the first question, but could you discuss how the shared symptomification would look different from the current one, especially in terms of like the cohomology theory that it can use?
Okay, thank you. Right, so there is a shared symptomification, and the shared symptomification maps to the shared the shared one maps to the non-shared one. So let's say, well, sorry, maybe I can just say it in words. The general heuristic, which is can be turned into theorems and precise examples, is that the pullback functor from the prismatization or the shared version, from the prismatization to the shared version, is fully faithful at the derived level. So you don't see more cohomology, but you do see new sheaves. And the same happens for the symptomification. And so symptomic cohomology would be the same, but you would see more objects, more crystals in the shared sense than in the non-shared sense. And the typical example of what happens is easy to describe. So let me give you the example. So if you think about SPUF ZP Hodge state, the usual Hodge state stack, this is BGM sharp. And this receives the map from the shared version. We have to be slightly careful when P is 2. And this is BGM sharp hat. And so in terms of quasi-coherent sheaves, quasi-co over here is quasi-co of A1 formally completed at the FP rational points of the FP rational points of the special fiber, so 0 through p minus 1. And quasi-co over here is just quasi-co of A1, no conditions. So the notion of sen operator that you get in the shear story has no nilpotence constraints. And that's why you see more sheaves. And this was also somehow this is something you could have guessed from the Kersig P picture, right? Like the sen operator integrally is the sen operator is an integral analog of the Higgs field. And what I'm saying over here is that the Higgs fields that show up in the shear story have no nilpotence constraints, whereas the ones that showed up in the non-shear story were forced to be nilpotent. And the same thing happens in the other stacks.